So hot, it can boil iron. So noisy, it can even waken the dead. Yes, rocket testing is a dangerous and quite intense process. But have you ever thought about what usually happens at a typical modern rocket testing facility? Whether yes or no, today we've got you. Come along as we get all fired up for a look at how space rockets are tested. April of 2021 has marked the 60th anniversary since Yuri Gagarin fired the first manned flight into the moon. Okay, so from that first experience, you might be tempted to think that humans now have a better knowledge of rocketry. To your dismay, the reverse is true. There is still a long way to go. New rockets from SpaceX's awesome Starship to NASA's moon-bound space launch system Giant are just mightier than anything attempted during the old-school space race. And still, there are different mission priorities these days and even different fuel sources. As such, the latest generation rocket engines by Elon Musk's mighty Raptors or the RS-25 from the shuttle program need to be properly checked and tested before they're trusted with the space journey and even delicate human life. The test conditions available are usually described as sea level ambient or altitude. This distinction is critical because air pressure is greater at sea level than several miles up above the ground. At altitude, rockets produce more thrust and thinner air and have to cope with less heat transfer, and these factors have major engineering implications. The ambient atmospheric conditions surrounding the test area work fine. Even though better simulations are provided by altitude test facilities, testing rockets at altitude is a lot more challenging, as technicians need to simulate conditions way up in the blue sky and not on the ground, where they can actually analyze them. For this, rockets are placed in a sealed chamber where pressure is sucked out with a mechanical pump to around 0.16 psa, roughly equivalent to the prevailing conditions 100,000 feet above sea level. And being that this is a sealed environment obviously creates its own problems. A process known as inerting is produced, whereby gases, nitrogen, and helium is fed into the chamber to prevent explosive buildup of rocket exhaust matter. Liquid rocket engines are typically fired in a vertical position, as gravity is all part of the fuel intake process. Solid rocket engines alternatively can be fired horizontally, which requires a smaller and cheaper flame trench. However, this comes with its own issues, noise and related issues, and we'll come to that shortly. So, where on earth are these testing grounds found? Most modern rocket testing facilities are situated in the southern United States in order to be near launch sites, which themselves are frequently close to the Earth's equator. And just before we forget, why are launch sites near the equator? Well, the land around the equator moves at around 1,670 kilometers per hour, while halfway towards the poles, land only moves 1,180 kilometers per hour. This implies that launching from the equator helps spacecrafts blast off already 500 kilometers per hour faster without any additional input of energy. Quite impressive, right? As such, SpaceX has a large rocket testing facility in McGregor, Texas, which is handy for the company's Boca Chica launch and assembly site. For today, let's put more emphasis on NASA's John C. Stennis Space Center in Hancock County, Mississippi. This is where new SLS rockets are being tried out in preparation for their first Artemis launches later this year, part of an ambitious program to put the first woman and next man on the moon in the next 3 years. Stennis has a fine pedigree in this regard, as it is where rocketry for the first and second stages of the Saturn V lunar landing were tested back in the 1960s. The magnificent landmark A and B test strands are even registered as official National Historic Landmarks. From 1975 to 2009, Stennis also tested the main engines that powered the 135 missions, not the iconic NASA Space Shuttle. Indeed, those same RS-25 engines that powered the shuttle, with some choice upgrades naturally, will hopefully be sending the SLS to the moon soon. The facility is so integral to American space lore that it's said by proud Stennis workers, if you want to go to the moon, you first have to go through Hancock County, Mississippi. Stennis is indeed perfectly situated for rocket testing because, for one, it's isolated from major population centers on a 13,800-acre site surrounded by a 125,000-acre buffer zone. Again, there's great access by road and 7.5 miles of specially dug canals, plenty of local water, a supportive local government, and a climate that suits testing, at least when hurricane season isn't in full swing. Alright, what usually happens in the actual test? During the most recent SLS warm-up at Stennis, a variety of rocket systems were checked over. Model testing is a way of assessing the overall structural integrity of components, essentially by striking them with a finely calibrated mallet and measuring their resonant frequency. If the frequency is off in some way, it could suggest faulty welds, cracks, or other problems that might jeopardize the ultimate mission. There's a so-called power-up procedure that must be followed to make sure everything comes on correctly and in the right sequence. The avionics, that is onboard mechanics and electronics, must all be tested and thrown with phony curveballs to reveal any unforeseen weaknesses. A crucial aspect of rocket avionics is the gimbaling system, which orients the rocket boosters in order to maintain overall trajectory. The system has its own self-contained hydraulics and must be tested thoroughly. A series of simulated countdowns will take place, ramping up to the so-called wet dress rehearsal, where propellants are flowed into the engine but not ignited. To facilitate the SLS test at Stennis, some 700,000 gallons of propellant, that's 200,000 gallons of liquid oxygen, and 500,000 gallons of liquid hydrogen are piped in from 6 floating barges, that's about 114 tanker trucks worth. At the moment of ignition, when the rocket does finally fire, technicians need to keep an eye on some fairly hair-raising physical changes to the rocket. With temperatures ranging from -400 degrees Fahrenheit thanks to the liquid fuel source, then rising to a few thousand degrees Fahrenheit while alight, the metal tank can grow and shrink by several inches. That internal exhaust will then jet into the flame chute, requiring 2 separate water suppression systems, both fed by a dedicated 66 million gallon reservoir. In addition to 240,000 gallons of water being pumped every minute over the chute to cool the engine exhaust during testing, some 92,000 gallons of water a minute are sprayed through a separate nozzle system to suppress noise. This noise suppression isn't just to help the local property prices, but it's to prevent all that acoustic energy disrupting the finely calibrated test equipment or affecting the material performance of the rocket itself. Those gigantic plumes of white smoke you see emanating from Stennis testing rigs are in fact steam from that colossal torrent of much-needed cool water. Stennis has its own high-pressure industrial water facility to manage this aspect of its operation, and a high-pressure gas facility, or HPGF, that helps pump gaseous nitrogen into the core state during testing. And this prevents outside air from entering into the testing zone during those all-important altitude tests. On the mechanical side, special software is also deployed during testing to control the avionics and simulate different atmospheric conditions the rocket may find itself subjected to. Software is believed to be the reason French rocket Ariane 5 suffered a disastrous mid-air mishap in June of 1996, so there's a lot at stake here. All these processes working in concert should help run a test that produces, in the case of the SLS, 1.6 million pounds of thrust, or 2 million pounds at altitude, consuming as it fires some 2.6 million liters of propellants. Thrust is measured using the TMS, which uses a series of load cells to calculate how much upward movement the thrust generates. With fuel weight taken into account, one rocket firing is complete and the real work begins. Some 1,400 sensors arrayed across the testing site produce terabytes of data which technicians can lore over in order to make subtle refinements ahead of the big launch. The impact of rocket launching, in particular at Stennis, goes far beyond just firing payloads into space, by the way. Anyways, we hope you enjoyed our video. For more of such amazing and informative content, please subscribe to our channel, give us a like, and share the video. And don't forget to turn on the notification bell for timely updates of our new uploads. We value your feedback. Don't forget to share your thoughts with us in the comments section down below. Thanks for watching. Bye.